Hello. All right. This is the last one for Time Zone 1, which is HL Paper 3. It's been over 24 hours, so like all the other exams, I can now talk about it. So here we go. Like I said, paper 3 is a little bit weird because they'll just throw whatever at you. But luckily, they're extremely guided. And so from the ones that I've done so far, which is all of them, they actually haven't been so bad. But anyways, here we go. A polygonal number can be represented as dots arranged in the shape of a regular polygon. Okay, yeah. So you have numbers, and then if you had the amount of dots that number was, then it could make a regular shape. So for example, these are triangular numbers because you can arrange them into a regular triangle. And then these are square numbers. These are pentagonal ones. Really? I'm sure, whatever. Okay, anyways. For any r-sided regular polygon, the nth polygonal number can be given by this formula. Oh, okay, sure. And then the questions actually start on the second page. So hence square numbers, you have this one. And then for triangular numbers, we just need to verify that it's gonna be this. So in other words, we're gonna use the general formula that they gave us for triangular numbers, which means that r is 3. So p3 of n is equal to 3 minus 2, so then that's n squared, minus, it becomes a plus, n over 2. So 3 minus 4 is -1, and then minus -1 becomes a plus 1, and then this becomes, if you factor out the n, exactly what you needed to show. Okay, next up. This is a triangular number, determine which one it is. So in other words, we set this equation that they give us in part 1. And then we solve for n. And then that's easy enough to do, especially because paper 3s, you have a GDC, so I'm not going to even bother factoring it. We can just solve it. I'm going to solve it by graphing. So n plus 1 over 2. Oh, oops, this should be x as a function. And then what did I want? 351. So the 26th polygonal number, as you can see from our intersection. So 26. Okay, now we're going to show that p3 of n plus p3 of n plus 1 is, well, an identity of n squared plus 1. Okay, so easy enough to do. P3 of n is just this expression. P3 of n plus 1 is going to be n plus 1 times n plus 2 over 2. Okay, and then we can add these together. So we got n squared plus n squared plus 3n plus 2 over 2. And so what do we got? We got 2n squared, we got 4n plus 2 divided by 2. And then we can divide all the terms by 2. And then this factors into this. Okay, showed that, that's nice. State in words what identity given in part BI shows for 2 consecutive triangular numbers. So I just have to state what this means in words. the sum of two consecutive triangular numbers is the square of the... I don't know what they're really looking for here. Is the square of the... I don't know, sum of two consecutive numbers, n plus 1 is the square of n plus 1. I'm not entirely sure what they want you to say here. It's only 1 mark. But okay, sure, whatever. For n equals 4, sketch a diagram clearly showing your answer to part BII. Okay. So I'm just showing the 4th triangular number, and oh, right here. So the 4th triangular number is 10, and then this one's 15. Let me just write here. So they're saying that 10, which is the 4th, plus 15, which is the 5th, should be equal to 5 plus 1 squared? Did I mess this up? Because on this side, I have 25, and then on this side, oh, whoops, n is 4. Ah, there you go. Sure? Oh, I was supposed to sketch this. What the hell? Okay. This plus... I really don't know what they want from you here. This plus this is equal to... Oh, I guess it makes a... Is this what they want you to say? The sum of two consecutive triangular numbers is a square number? Is a square number? Sure. Okay. And then there you go, right? This is 5 squared. This one is P35. This one is P34. Okay, I think that sounds good. That looks good. Okay, next up, show that 8 times P3 of n plus 1 is the square of an odd number for all positive integers. Okay, so this is P3 of n. So if I multiply this by 8, and then I think they said add 1, I need to show that this is an odd, the square of an odd number. Okay, that should be easy to sort out. This becomes 4, so then we have 4n squared plus 4n plus 1, and then this is equal to 2n plus 1 squared, and then basically you guys should know that 2n plus 1 is, if n is an integer, is the expression for an odd number. So for n being this, 2n plus 1 is odd, and then That basically means that 8p3 of n plus 1 is literally the square of an odd number. Sure. Okay, cool. We've related triangular numbers to square numbers. Okay. And then now we do pentagonal numbers. They can be represented by this arithmetic series. Hence show that p5n is going to be this. Okay. I'm going to have to copy this again. Okay, so let's see. So because it's a series, I think we're going to use the arithmetic series formula. To show that this is going to become this. So we need to find un, which is the first term, so that's easy. That's 1. And then the last term is right there, so this is un. So plus 3n minus 2. And this is basically it, right? We just make the 2 go entirely in the denominator, the n stays in the front, and then the 1 minus the 2 becomes the minus 1. Nice. Okay. By using a suitable table of values or otherwise determine the smallest positive integer greater than 1 that is both a triangular number and a pentagonal number. By using a suitable table of value or otherwise. So we want to find out when this is also going to be a triangular number. So I guess if you have that function in your graphing calculator where if you tell it a function and then it can do like a step-by-step calculation, then you can do that. Or you can graph both expressions and then the triangular number expression, find out their intersection. That works too. You know what? Let's do it their way, except oh shoot. Do I have Excel? I mean, I have Word. Aha, okay. Check this out. So we have 1, 2, and then these are going to be the n values. So I don't know, I'll just populate this. And then these are going to be my triangular numbers. So that formula was n times n plus 1, which is the next number, divided by 2, I think, right? I wonder if this is going to work out. But we'll try it out, because they're saying use a table. But it does say otherwise, so yeah, it would have been faster if I just graphed them. But this is just for curiosity's sake. Okay. And then we can just populate this. And then we have our formula for the pentagonal numbers, which is n times 3 times n minus 1 divided by 2 again, right? Reference. Okay. and then fill this out. So first, let me just double check if this actually gave me the right numbers. I should have 1, 3, 6, 10, 15. Yeah, that looks good. And then 1, 5, 12, 22, 35. Nice. Okay. Anyways, so I'm trying to find out the first value of n that isn't 1. That's both a triangular number and a pentagonal number at the same time. So I'm just checking each table. And seeing which triangular number is here. This is stupid. Why would they ask you to do it this way? Am I just blind? I'm trying to find something that's a triangular number and a pentagonal number. I mean, I guess I could just graph it and do this the faster way. Screw this. Oh well, that's still so stupid. Why would they ask you to do a table? Okay, I'm finding out where these intersect. So 0 and 1, obviously. Actually, no, I guess I can't do it this way, because this is saying when for the same n is it going to be both triangular and pentagonal? Wait, isn't that what I want to find out? That's both triangular number and a pentagonal number. Okay, shoot. I shouldn't have closed that Excel sheet. Yeah, this isn't going to tell you it because it's going to be different values. You're not finding out like the same exact value. That's so dumb. Okay, I don't want to spend time looking for it, but basically, once you filled out your table, wait, no, this is not the right one, is it? This one takes me to edge. Once you have your triangular numbers, you are looking for which triangular number is also a pentagonal number. And then whatever n value that is the answer. I guess for the sake of everyone curious, I should do it. Because that's why you're watching this. Okay, let me just populate my ends. Oops. This is why I have background music. Alright, and then I guess you just eyeball this. Let's see, conditional formatting. Highlight cells that are equal. Does that work? That did not work. I'm sure there's an Excel function, which is what I'm trying to do because I really don't want to look and see. Highlight duplicate values. Aha. Right there. 210. Wow. Why did I not see that the first time? So n being 20. Because if n is 20, it gives you a triangular number 210, and it gives you a pentagonal number 590. But 210 is also a pentagonal number, so that's what they want. How far down was that? That was the 20th number. Wow. Okay. Alright, and then we're not done, but this is the last question. So, any polygonal number can be represented by this series. Use mathematical induction. Okay, sure. So, the base case though is for n being 3. Or r being 3, rather, as you can see here. Okay, so then this is the sum from m equals 1 to n. And then we have 1 plus m minus 1. And then r is 3, so 3 minus 2 is just 1. Okay. And then if you really wanted to reason this out, then this is gonna be, I always like to write the first few terms so that I can see what exactly I'm doing. And then this one is 1 plus 1, 2, and then 1 plus 2, 3. Okay, so essentially this is going to be the sum of the first n terms. Your first term is 1, and then your common difference is 1. So I'm using this sum formula, and if I manipulate this, it should look like that. And then P3 of n. Again, we already know that this looks like n squared plus n over 2. So what do we got? I got n over 2 over here. I got 1 plus 2n minus 2. This does not look the same. let me just double check that I got the right numbers here. Oh, I messed up the formula. Oops, my bad. This is 2 times T1. So this is 2 plus. There you go. Okay. Again, this is equal to the there you go. My bad, my bad. Okay, yeah. So using the proper sum formula, simplify, and then you should get that left side equals right side, so we know it's true. Then we assume true up to n, or r equals k plus, or r equals k for some positive integer k. So that means that this for r being k is true. So m equals 1 to n of 1 plus m minus 1. What was it? K minus 2? And then this is going to be equal to k minus 2n squared minus k minus 4n over 2, I think. Substituting k in for r in here. Okay, so we know that this is true, and then for r being k plus 1. Okay, k plus 1 means that we'll have this k minus 1 and then we want this to show up in there. Not really sure how. And then we want it to look like this, but for k plus 1 instead of k. So we want k plus 1 minus 2, which is k minus 1. And then k plus 1 minus 4, which is minus 3. Yeah. Okay. So this one's slightly trickier because normally they're nice and like the summation is the thing that you split up so that you can get your hypothesis in there. But let's see what we can do. We do need a k minus 2 to show up, so that we can use that. Alright, I guess I'm forcing a k minus 2 to show up. So this is the same as k minus 2 minus plus 1. right? I need a k minus 1, or I need a k minus 2. So I'm gonna rewrite the minus 1 as a minus 2 plus 1. And so if I multiply this into these guys, and then these guys, then I'm gonna get my 1 plus m minus 1 times k minus 2 plus m minus 1. Okay, and then this is easy. We can split up our summation, or rather, I can split up my summation into the separate terms. These guys are my hypothesis, so I can replace this with my assumption right here. And then essentially all I need to do is sum the last term. So sum this up. For those that can't recognize what this is, like I said, I like to write out the first few terms just so that I get a feel for it. So if m is 1, then this is going to be 0. And then if m is 2, it's going to be 1, 2, 3. So this goes all the way to n minus 1. Okay. 1, 2, 3. All right, so this means that we have, if you ignore the 0, we have u1 right here. This is just another arithmetic series. You have d, your common difference is 1. There's lots of ways to do this, by the way. And then the number of terms you have for this sequence is not the same n minus 1. Okay, so this is going to be n minus 1 over 2 times 2 minus n minus 1 minus 1, which is minus 2. Okay. And then again, just let me remind myself what I want. All right, so if I combine these two terms together, I think I will get what I want. After some manipulation, of course. What was this, 5 minutes? Oh well. 2, and then from this stuff right here, what do I got? 2 minus 2. So then I have plus, multiply the n in, plus n squared minus n. Ah, okay. Looking good. And so if I collect my like terms, I think I get what I want, right? Collect my n squareds. So I would add these two coefficients of n squared together. So that gives me my k minus 2 plus 1, which gives me my k minus 1 squared. So that looks good. Oops, not the squared, n squared. And then let me change my pen. Okay, whatever. Aha, okay. And then if you collect these coefficients together, technically it's a +4 minus 1, which gives you a +3, and then you factor out the negative again, which gives you this. Anyways, just collect your like terms. Okay, and then we're done, right? Of course, you have to say it's true, therefore by induction, blah blah blah. But anyways, there you go. Okay, first one done in 20 minutes. And that was 27 marks. So I got 7 marks, or 7 minutes to spare. It's about a mark a minute, by the way, if you didn't know the ratio for marks to minutes. Okay, and then this question asks you to explore cubics in this form. And also cubics with 1 real root and 2 complex roots in this form. Alright, in parts A, B, and C, R is going to be 1, A is going to be 4, B is going to be 1, and then consider this equation right here. Sure. Given that 1 and whatever are the roots of the equation, write down the third root. Okay, easy enough. It is the complex conjugate to the other complex root. Verify that the mean of the 2 complex roots is 4. Okay, that should be pretty easy. So you add the 2 complex roots together, divide it by 2, and well, you get 8 divided by 2, which is 4. Okay, don't know why they're asking us that, but 2 marks. Consider this function. So now we're talking about real polynomials. Show that the line x minus 1 is tangent to the curve at the point 4, 3. So this is a pretty standard calculus question. So we can find the derivative. Actually, you don't even need to necessarily find the derivative because we have a graphing display calculator. We just need to evaluate the derivative at 4. And so you don't need to manually take the derivative. Your graphing calculator can do that if you know what the function is. I can do that also on Desmos. So f prime of x was x minus 1 times whatever it is, x squared minus 8x plus 17. Okay, and then tell me what the derivative is at 4, which is 1. By GDC. And then of course we just need to know the equation of the tangent line, so we can start with point gradient form. And then rearranging this, we get y equals x minus 1. So as you can see, y equals x minus 1, right there is your tangent line. Okay, and then sketch the curve of f and the tangent of the curve at point A, clearly showing where the graph crosses the x-axis. Oh, so right there. So you just sketch this out, clearly showing where it crosses the x-axis, which is also where the actual function crosses the x-axis. Okay, there you go. Alright, consider the function. Now, in general terms, b is positive. Hence show that g prime is going to be this. Well, okay, I was trying to avoid taking a derivative, but now I cannot. What's the best way to do this? I'm going to use the product rule. Okay, so take the derivative of this, multiply it by this. So I think that gets me the second term. 1 times this will give me that. And then I'm gonna take the derivative of the second factor, multiply by the first factor. So I got 2x minus 2a. And then of course, as you can see, if I just factor out the common factor of 2, I will have it right there. Okay, so then this, rearranging and factoring out the common factor of 2, gives me what they want me to show. Hence or otherwise, prove that the tangent line to the curve G at this point will intersect the axis at point R. Okay, it says hence. So I guess we're gonna do the same thing that we did here, just with variables instead. So at point P, what was the point? A. And then we got G of A. Okay. So G prime at A, we are going to evaluate. So if X is A, this first term is going to be 0 because of this factor right here. A minus A is going to be 0. And then in this one, I will have a squared minus 2a squared plus a squared plus b squared. And then, oh, this is nice. These all cancel. So G prime at A is B squared. Okay. Now, what is G at A? G at A is going to be A minus R times B squared. This is because I'm plugging in A into this part, which I already did right here in this part, so I already know it's going to be B squared. Okay, so the equation of the tangent line is going to be y minus all of this stuff, which is the y value, B squared times A, or oops, X minus A. Okay, and then I want to find out that this is going to intersect the x-axis at R. So then if x is 0, I can just show that y will be 0. Sorry, if x is R, I can just show that y will be 0. Okay. So y, and then I'm going to move that term over to the other side. I'll have r minus a, and then this is going to be plus b squared a minus r. Okay, and then you can expand this out, collect like terms, but these are literally just opposites of each other. So y is going to be 0, i.e. let's just summarize this, i.e. the tangent at a and g of a will intersect the x-axis at r and 0. Okay, so I think what this is trying to say is no matter what, this tangent line is going to have the same x-intercept as the actual function itself. So what we can do is you can just kind of verify this by adding your own little slider on Desmos, and as you can see, woo, it's always the same. Okay. Then we move on to complex equations. This equation has roots r because of the first factor, and then two complex roots. Deduce from part di, the derivative, that the complex roots of this equation can be expressed like this. Okay, these two are the exact same equation, which means that all I need to show, because we know that this has these complex roots, a plus bi, and they're just saying that you can express those complex roots like this. So if you compare the two, all I basically need to show is that the square root of g prime of a is going to equal to b. And then as you can see right here, I already know that g prime is b squared, which means that the square root of g prime of a is b, and then you're done. Because that means that this is b. 1 mark, yeah. Okay, and then what is happening? Okay, on a Cartesian plane, let C1, C2 represent the real and imaginary parts of the complex roots of the equation. Okay, for the diagram shows a particular curve. Blah, 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 blah. Use this diagram to determine the roots of the corresponding equations of this. Okay, well, the first root is right here, right? So z equals -2, because as we've established, the first root is this intersection. And then the other roots are in the form a plus square root of g of a, like that, like this. Okay. Which means that a is a, right? Okay, we don't know what a is. And then, do I need to find a? I think I need to find a. Okay, whatever. I'll deal with a later because that looks like a pain. And then this is the tangent. This is just the tangent gradient. which we don't need calculus to do because we have the straight line, and we know that this has a vertical, well, delta y. Let me change that to a brighter color so that you guys can see, or I'll change it to red once I can. Okay, so this has a delta y of 80, and then it has a delta x of basically a plus 2. Okay, so that means we can write this in terms of a as a plus I to the square root of 80 over a plus 2. Then I need to know what a is gonna be. So I know if I plug in a into the function, I should get 80. And I also know that r is negative 2. Okay. So what this is saying is that a plus 2 times a squared minus, oh wait, this all cancels out into to be 16 because we saw that before. This is 16. This needs to be 80. Right? I plug in a, I should get 80, the y value 80. So a is, what's 80 divided by 16? That's not a nice number, is it? Oh, it is. 5. So a is 3. Okay, so that means that my complex roots are going to be 3 plus or minus the square root of 80 divided by 5. 80 divided by 5 is 16, so this is going to be 4. Sure, okay, yeah, there are your roots. And then state the coordinates of C2. So C2 is A and negative 4. Oh, sorry, A is 3. Okay, not too bad if I'm doing this properly. Okay, and then consider this curve. So as long as a is not r, these points in r as defined in dii. What the heck is dii? Sure, okay, yeah. The curve has an inflection point at P. Show that the x-coordinate of the inflection point is this. Okay. Where the heck was my derivative? I'm gonna just take the second derivative and we'll deal with that when we get there. So this is my first derivative. Oh, and we don't need to demonstrate a change in concavity, so that's nice. Okay, so here's g prime. Take the double derivative. I'm going to take the derivative of the polynomial part at the end. So that's 2x minus 2a. And then this one is going to be a product rule. So I'm going to have 2, basically x minus a plus x minus r. Again, the derivative of this is 1, so this is going to be that. Derivative of this is 1, so you just multiply it with this to get that one. And then what do we got? We got 4x minus 2a minus 2r plus 2x minus 2a. And then at the inflection point, p, so at p, this should be equal to 0. So what do we got? We got 6x minus 4a minus 2r, which means that 6x is equal to 4a plus 2r. And then divide everything by 6. And then you'll get that after you reduce and divide everything by 2. And then that's what we want to show, right? Yeah. Okay, we're done. Hence describe numerically the horizontal position of point P relative to the horizontal positions of R and A. What? Okay. Wait, this is only one mark, right? Okay, so point, I think, what was it called? R? Capital R? Has a horizontal position of R. Then we have this one right here, which is point P, which has, or point A, has a horizontal position of A, and then somewhere in between we got point P, which has this horizontal position, 1/3 of 2A minus, or sorry, plus R. And then how do I describe where it is in relative to them? Okay, let's find the distance in between them. So this distance is going to be 2/3a plus r/3 minus r. So I'm subtracting the 2. So then I'll have 2/3a minus 2/3 r. So this is 2/3 of a minus r. Oh, okay, yeah. And then this is the distance. A minus r is this distance. Okay, okay. So it's saying that from R, capital R to P is 2/3 of the distance of R to A. And then P is obviously then 1/3 of the distance from P to A. Or from R to P. Okay, yeah. So I think you can just, I don't know how they want you to say this, but you can say that RP to PA is 2:1, something like that. Okay. Consider the special case where A is R. Sketch the curve. Can't you just graph this? Well, if A and R are the same, then don't they just like overlap? So before I check this, because I think the graphs look like this, right? Like woo, and then woo, whoops, no, not right there. Like there. And then this is R, and then this is A. So then if they end up being the same thing, then your wave is gonna kind of squish and conform so that it'll look like... Oh, and then you also have the inflection point P somewhere here. And if R and A are going to converge, then P will also converge together. This is kind of like a funny squeeze theorem for those that know what that is. And they will just eventually look like that, I think. But that's just my prediction. You have a GDC. You can just literally let's just plug in these values and see if I'm right. A, R are 1, B is 2. Okay, so R is 1, and then I'm going to change this formula to 2ax plus a squared plus b squared. And then A is 1, R is 1, and then what did they want B to be? 2. Okay, so B is 2. There you go. Which is more or less what I drew. And then we know that this is at 1, of course. And then for A equals R and B is positive, state in terms of R the coordinate points of P and A. So A is going to be R and then G of R. But it's the intercept, of course, so then this is just this is R and 0. And then also the inflection point becomes the same point as well. So this is R and 0, I think. Let me scroll up in case my camera is covering what I'm writing. Right? Basically all three of these points, if A goes to R, they will all become here. Whoa, look at this. Wavy. Okay, well, that's it. I'm done. That was a pretty easy paper 3, in my opinion. Yeah, I don't know. Nothing else to say. Thanks for watching, I guess. And yeah, I don't know. Maybe I'll do TZ1 2 once it gets officially released by IB. Otherwise, congratulations. Well, not mine, because you're not mine, but congratulations, TZ1 HL students. You made it. Or maybe you didn't, but at least you're done. Okay, thanks for watching.